Yes, good evening to you all. Welcome back to another presentation on time domain specifications of second order system we are discussing about. By the way, today we will see the lecture number 33. Lecture number 33. Today we will see the another important specification, that is almost all the last specification for the second order control system, that is the settling time. The settling time. The settling time. So T suffix S, that is what? So T is the time, S stands for settling. So this is called settling time. What is a settling time? As we have discussed in our previous presentations, if you recall, the time response of a second order system, just we recap the second order system. For a second order system, we have the time response, that is C of t versus t. This is t. Okay, let us call this is your 100% line, that is 1. If you draw the graph normally like this, you will have. This is the basic time domain response of a second order control system, in which we have seen this is the 0.5. Here it is called a specification. First specification what we have seen is T suffix D is the delay time, and at 100% means the time required for the waveform or for a response to reach 100%, means 100 by 100, it is 1. So here the time it is called as TR, rise time. Similarly, this is the peak, and to reach the peak value of the response, that is called TP, peak time, means the time required for the waveform to reach the peak value is called peak time. And also we have seen in our previous presentation, that is maximum peak overshoot. So that is the gap between this one, the peak value to the from this line 1. So this is the difference actually. This is called peak overshoot. And the settling time now is nothing but the time required for the waveform to settle within a specified tolerance band. There is a tolerance band here actually. Okay, actually this is the line, unity line, you can call it as C of t value is 1. With a reference of this 1, with respect to this, you have some tolerance band line here. Tolerance band. Normally error band, this can also be called as error band. Normally this is 2% to 5% of tolerance. Actually, the tolerance band is having the limitations or the values 2% to 5%, 2% to 5% of tolerance band. Within this band, the response will be settled. So from where you can have a constant value. Therefore, here from the time at which the waveform settles, that is called settling time. This is T suffix S normally. Clear? So from starting to 0 to the the time at which or from which the waveform settles, like it is a constant line we will have from there onwards. So that from that that period is called as settling time. So in this presentation we will see what is the mathematical expression for TS. Is there any mathematical expression for it? Yes, definitely we have mathematical expression for TS. We will see that. Clear? So this is the small representation of the response of a second order system. Now let us go for the mathematical formula of TS. So normally from this graph we know that the response of a second order system can be given as C of t is equal to 1 minus e power minus zeta omega n into t by under square root of 1 minus zeta square into sine of omega d into t plus theta. This we know already. This is the response. We must remember this all the time. Whenever we are discussing or studying about the time response of a system, you must remember this. C of t is equal to 1 minus e power minus zeta omega n into t by under square root of 1 minus zeta square into sine omega dt plus theta. Normally, if you see this, if you observe this, this particular is an exponential component. This is the exponential component. This is the sinusoidal component. So, in order to find out the mathematical formula for settling time, normally the exponential component will be considered. This plays very important role actually. The decay function, this is called decay exponential function. This is the sinusoidal function. This is very important basically. So for this what we have to do, let us consider this exponential term and then equate to the tolerance band normally. Okay, then so what is the exponential form? This is what this factor is, exponential function. This is the sinusoidal function. So now the settling time t suffix s for 2% of tolerance band. Okay, tolerance band. Okay, the settling time for 2% of tolerance band, what will be the expression? Then simply you equate this particular exponential function to 2%. Then what we will have? Let us see. So that is nothing but it is e power, that means e power minus zeta omega n into t by under square root of 1 minus zeta square. This is the exponential term that you should equal to 2%. Means how much? It is 2 by 100. It is 0.02. Clear? Take natural logarithm on both sides, or otherwise one more consideration we have to consider here, means for the least value of zeta, assume that the zeta value is very small, or you can write this for small values of zeta. For small values of zeta, this particular expression means that for small values of zeta, you can ignore this denominator part. Square root of 1 minus zeta square can be ignored. Then you just consider this numerator part only, means e power minus zeta omega n into t is equal to 0.02. Clear? So for small values of zeta we are considering. Clear? Then you can ignore this. It can be ignored. Then take the natural logarithm on both sides, because exponential is there. In order to minimize the exponential, then take the natural logarithm on both sides by taking natural logarithm by taking the natural logarithm on both sides, then what you will have? ln. Clear? I will erase this for a moment. So that is nothing but, for this, nothing but ln of e power minus zeta omega n. Remember that at t is equal to ts. Remember that. Means we are aiming at to find out ts. Then in this expression you substitute in place of t as ts. Okay, as we have substituted in previous presentations. So it is ln of 0.02 natural logarithm. Then this natural logarithm ln and then exponential will be cancelled out. Then what you will have, you know, you will have minus zeta omega n into ts is equal to, clear, ln and exponential will be cancelled out and minus zeta omega n ts will be there here, and ln of, if you calculate from your calculator, scientific calculator, this value you will get minus 4. It will come minus 4 it will be. Clear? Then so on both sides the minus sign is there, means here is minus, on right side also minus, both will be cancelled out, and from here you can say that, from this you can write ts is equal to 4 by zeta times omega n. This is the formula for settling time. All time in seconds only. In seconds only. The units are in seconds only. Therefore, ts, settling time, is equal to 4 by zeta omega n seconds. This is for 2% of tolerance. 2% of tolerance band. Clear? And remember that this 1 by zeta omega n is called, here 1 by zeta omega n is called time constant. This is called time constant, and it is denoted by the letter t. Therefore you can write this ts is equal to 4 times t. If 4 times t, 4 into t basically, or otherwise you can remember this formula, 4 by zeta omega n. This is the settling time formula for 2% tolerance. Similarly, you can write for 5% also. Similarly, for 5%, everything is common. Only the thing is, you just take natural logarithm of 5%. The everything will be same as we have seen here. Okay, so we can do the same for that also. Okay, simply I can, so for similarly for 5% of tolerance, 5% of tolerance band. Okay, the error, everything is same. So here also the same actually, ln of e power minus zeta omega n ts, everything is same. Only thing will change, ln of 0.05 only, means 5%. It is 5%, 5 by 100. 5 by 100 is nothing but 0.05. Here also same. This will be cancelled out, and this implies minus zeta omega n into ts. If you apply, if you calculate this, and it is minus 3. It comes minus 3. Therefore, these both will be cancelled out. Then you will have from this ts is equal to, it is 3 by zeta times omega n seconds. This is the settling time for, this is for 5% of tolerance band. This is the tolerance band. So these are the very important formulas actually. So let us summarize. With this, almost all we have covered all the time domain specifications basically, and these are the settling time formulas basically. Yeah, so it is if you remember these and if you practice, no, it will be very useful. And I will summarize for you. So what are the time domain specifications we have seen? In summary, you can write like this: summary on time domain specifications. Time domain specifications. So summary is nothing but till now what we have seen. First one is we have seen the delay time. We have seen the delay time. It is T suffix D. What we have seen basically, delay time is nothing but the time required for the response or for the output to reach 50% of its final value. That is the definition. Okay, for this, what is the mathematical expression we have seen from that linear approximation? Okay, then TD is equal to, what we will have is 1 plus 0.7 times zeta by clear omega n seconds. Omega n 1 plus 0.7 zeta by omega n, that is the delay time. And what is the second we have seen? Rise time. The second parameter what we have seen, the second specification, T suffix R, rise time. What is the rise time we have seen? Rise time is equal to, it is pi minus theta by omega d. This is what we have seen, omega d. And further it is pi minus theta is nothing but tan inverse of square root of 1 minus zeta square by zeta by, what is omega d? It is damped natural frequency. If you convert in a natural, the formula is that omega n into square root of 1 minus zeta square. That is the formula. Seconds, all are in seconds only, and that is the second parameter. What is the third parameter? Peak time. What is the third one? Peak time. It is T suffix P, and this is equal to simply pi by omega d. Pi by omega d. So this is further pi by, what is omega d? Omega n into square root of 1 minus zeta square seconds. Clear? And what is the fourth one? That is the maximum peak overshoot. Maximum peak overshoot, that is percentage of MP. Percentage of MP is equal to, what we have seen, e power minus zeta pi by under square root of 1 minus zeta square into 100. Clear? Into 100. Maximum peak overshoot. And the final fifth one is the settling time, that I will write here. The fifth one is the settling time. The fifth one is the settling time. That is T suffix S. This is 4 by zeta times omega n seconds. This is for 2% of tolerance band, and this is equal to, it is 3 by zeta times omega n seconds. This is for 5% of tolerance. Clear? So this is what your time domain specifications. With this, we will conclude the time domain specifications, and with this we will close today's presentation. And next presentation we will see some very important examples which have been asked in GATE examinations, as well as UPSC examinations, and in various state and central level competitive technical examination point of view, right? So I think you have enjoyed this, and you can share, and you can like it, and even you can comment, you can suggest, so that I definitely will take in positive and maximum try to improve for your benefit. Thank you.